determined by how many IOs some hardware is something that can decide various things. And then there's also the NCs that
안녕하세요. DFT 웨비나에 관심을 가져주시고 참여하여 주셔서 감사합니다. 이번 웨비나에서는 No Compromise 스캔 어프로치인 테센 스트리밍 스캔 네트워크를 소개해 드리고자 합니다. 본 웨비나는 테센트 프로덕트 매니지먼트 디렉터인 가이어가 진행하게 되며 한글 자막이 제공됩니다.
First, let's review some of the challenges we see in SoC designs today. The most common way of connecting core level scan channels to chip level pins is through what we call a pin-muxed approach, where MUX network decides which cores that are directly connected to the chip level pins. This is straightforward for a small design like this, but when the number of cores grows and when the complexity of the cores grows and when we get multiple levels of cores, this becomes more and more complex and sometimes suboptimal. And the reason for that is a lot of the constraints that we have to deal with. For example, how many cores you can test concurrently is determined by how many IOs you have available for a scan test. Also, which cores that are tested concurrently or which cores can be tested concurrently is a hardwired decision. It's something you have to decide during the design process. There's also dependencies related to the number of channels at core level, and that also again determines which cores you can test in parallel. And now you can build in some more flexibility in this approach with a more complex MUX network, but that also increases the potential for routing congestion related to routing all of the scan channels all across the design. Now there are also different ways you can deal with this. Now you can implement what we call a bottom-up flow, where you allocate a fixed number of scan channels like early in the flow. Let's say you decide to have the same number of scan channels for all of the cores and kind of make a lot of decisions early. That's the easiest approach, the least effort. But a side effect of that, you might end up wasting bandwidth because the different cores that you group together end up having different scan chain length or different pattern count. Now you can address that then by reallocating the scan resources, for instance, allocating fewer scan channels to the cores that require less data. That means reconfiguring compression, rerouting the scan channels, regenerating patterns, and this is a lot of effort. So you're dealing often with have to make a compromise between effort and test time. Furthermore, we also see that the pin-muxed approach is not very effective when we deal with large numbers of identical cores. You can broadcast the scan inputs to multiple cores, but typically have to observe all of the scan outputs for all of the cores. And there's also some challenges associated with multiple different pipeline stages, different number of pipelines for different cores. The throughput also is determined by the core shift speed. So even though you have a tester that can operate at a higher frequency, and even though your IOs can operate at a higher frequency, your shift speed is limited by what the cores can handle. And as we see more designs using a tiled approach, tiles with abutment, where you don't have this top-level routing layer, it becomes even more challenging to route scan resources to the various cores, because you have to go through one core to get access to the next. Tessen Streaming Scan Network, or SSN, is a new approach to distribute scan test data across an SoC. In this example, we see a design with 6 cores and an SSN bus. The SSN bus is a high-speed synchronous bus to deliver packetized scan test data to the cores. Part of the SSN network is what we call a host node in each core. This host node ensures that the right data is picked up from the SSN bus and sent to the scan inputs of the core. Could be compressed, uncompressed, or a combination of both. And also ensures that the scan output data is placed back onto the bus. The host nodes also generate the DFT signals locally, scan enable, scan clock, and so forth. Each node knows what to do and when to do it based on a simple configuration step that's done over IJTAG. This means that the groupings of which cores are tested together and which cores are tested sequentially, which cores are active, these decisions are not hardwired. They are fully configurable. The configuration is done as a setup step, one-time setup step per pattern set. Once this setup is done, all the data on the SSN bus is payload. The fundamental principle behind SSN is that core level and chip level DFT is decoupled. What that means is that the number of scan channels per core is completely independent of the width of the SSN bus, and as well as the number of scan channels at the chip level, and also independent of all the other cores in the design. This means that dramatically simplifies the planning and implementation effort, and it also allows you to make grouping and other decisions at retargeting time rather than design time. This architecture is very flexible. The bus width is typically determined by the number of pins, scan channel pins available. It could be as narrow as 1 bit. This architecture also eases routing and time enclosure since we eliminate the top-level test mode muxing, and it is also fully compatible with tile-based designs with abutment since no top-level signals have to be routed. SSN also contains many capabilities that help optimize test time and test data volume without having to increase the DFT or planning effort. SSN has capabilities to automatically tune how much data is sent to each core to help reduce the white space in the test data, and also has a capability to test multiple identical cores at constant cost while still have diagnosis support. And SSN is also proven in silicon. So how does SSN work? Let's take a closer look at the concept of packets and packetized scan test data delivery. In this little example, we have a design with 2 cores, Core A and Core B. Core A has 5 scan channels and Core B has 4 scan channels, 4 inputs, 4 outputs. Now a packet is defined as the total amount of data that is needed to perform one shift cycle across all of the cores that are tested concurrently. So since we are testing both Core A and Core B, the packet size in this example is 9 bits. Now at the same time, notice that the SSN bus width is 8 bits. And remember that the width of the SSN bus is typically defined by the number of pins available for test, completely independent of number of scan channels per core. Now, on the left side of the slide here, we see how data is streamed through the bus, through the synchronous SSN bus. Now, let's take a closer look at the first packet. Again, notice that to deliver all of the data corresponding to that packet, we need 2 cycles. On the first SSN bus cycle, we see that we are able to deliver all of the data needed to perform 1 shift cycle for core A, all the 5 bits needed. And so after that first SSN bus cycle, we can shift core A. But core B has to wait because it's the rest of the data, all of the data needed to test core B isn't available until we have we're at the second SSN clock cycle. And the SSN host, the host nodes, then know exactly where the data corresponding to that particular core is on the bus, and also when to pulse the shift clock. Now, if we look at the next packet, notice that the positions now are shifted, rotated. Again, this happens because we are able to fully utilize, pack all the data together. And also now, since we have 9 bits per packet and an 8-bit bus, that's why we see this rotation. So on the
안녕하세요. DFT 웨비나에 관심을 가져주시고 참여하여 주셔서 감사합니다. 이번 웨비나에서는 No Compromise Scan Approach인 테센트 스트리밍 스캔 네트워크를 소개해 드리고자 합니다. 본 웨비나는 테센트 프로덕트 매니지먼트 디렉터인 가이어가 진행하게 되며 한글 자막이 제공됩니다.
First, let's review some of the challenges we see in SoC designs today. The most common way of connecting core level scan channels to chip
The pace of digitalization is unprecedented, and it's completely transforming our world, harnessing new technologies across the landscape of industry to fundamentally change the way we live. Electronics will be pervasive as companies move from selling hardware to providing personalized digital services. IoT will connect everything with automation and intelligence to optimize performance. It's all enabled by digital threads that turn silo data into connected disciplines and processes. These threads form the neural network of a digital twin, a virtual entity which mirrors the physical world, turning data into insight to continuously design, build, and optimize throughout the product and production lifecycle. This transforms siloed electronic systems development, enabling intelligent simulations and parallel design to front-load quality control. Synchronizing data throughout the supply chain and manufacturing process improves productivity and allows manufacturers to diagnose potential obstacles and avoid them. An integrated lifecycle with requirements, planning, and execution in a single system allows complex products to be developed faster and with the full collaboration of all stakeholders. Siemens can help you achieve rapid digital transformation, powered by the world's most comprehensive digital twin. There's no need to dream about the future. It's already here.
안녕하세요. DFT 웨비나에 관심을 가져주시고 참여하여 주셔서 감사합니다. 이번 웨비나에서는 No Compromise 스캔 어프로치인 테센트 스트리밍 스캔 네트워크를 소개해 드리고자 합니다. 본 웨비나는 테센트 프로덕트 매니지먼트 디렉터인 가이어가 진행하게 되며 한글 자막이 제공됩니다.
First, let's review some of the challenges we see in SoC designs today. The most common way of connecting core level scan channels to chip level pins is through what we call a pin-muxed approach, where MUX network decides which cores that are directly connected to the chip level pins. This is straightforward for a small design like this, but
안녕하세요. DFT 웨비나에 관심을 가져주시고 참여하여 주셔서 감사합니다. 이번 웨비나에서는 No Compromise 스캔 어프로치인 테센트 스트리밍 스캔 네트워크를 소개해 드리고자 합니다. 본 웨비나는 테센트 프로덕트 매니지먼트 디렉터인 가이어가 진행하게 되며 한글 자막이 제공됩니다.
first, let's review some of the challenges we see in SoC designs today. The most common way of connecting
The pace of digitalization is unprecedented, and it's completely transforming our world, harnessing new technologies across the landscape of industry to fundamentally change the way we live. Electronics will be pervasive as companies move.
안녕하세요. TFT 웨비나에 관심을 가져주시고 참여하여 주셔서 감사합니다. 이번 웨비나에서는 No Compromise 스캔 어프로치인 테센트 스트리밍 스캔 네트워크를 소개해 드리고자 합니다. 본 웨비나는 테센트 프로덕트 매니지먼트 디렉터인 가이어가 진행하게 되며 한글 자막이 제공됩니다.
First, let's review some of the challenges we see in SoC designs today. The most common way of connecting core level scan channels to chip level pins is through what we call a pin-muxed approach, where mux
The pace of digitalization is unprecedented, and it's
안녕하세요. TFT 웨비나에 관심을 가져주시고 참여하여 주셔서 감사합니다. 이번 웨비나에서는 No Compromise 스캔 어프로치인 테센트 스트리밍 스캔 네트워크를 소개해 드리고자 합니다.